So in this video, I'm going to look at problem 26 from chapter 24. 26. So in this problem, we have three parallel plates that are parallel to each other, and they have some separations, and a voltage source is connected to them. So these plates form some capacitor. So let's first draw this. So I'm going to draw the plates using colored chalk, so we can actually tell the plates from the lines that I'm going to draw. So the separation of these plates is D1 and D2. Yeah, like so, and we have a voltage source, and it is connected to, so one terminal of the voltage source is connected to the middle plane, the other terminal is connected to one of these plates, and also to the other plate. Okay? I don't need to draw it this way, I could just draw it from the other side, but the same terminal is connected to these two outer plates, and the other terminal is connected to this inner plate. Right, so they're asking for the equivalent capacitance of this configuration. So first they're asking whether these two capacitors as formed are parallel or in series, and then they're asking for the equivalent capacitance and so on and so forth. So first of all, are they connected in parallel or in series? Okay, so let's start with that one. Well, the way to resolve this is to see whether they share a common charge or they share a common potential difference. Now in this case, they share a common potential difference. So this is providing some potential difference delta V. So the potential difference across these two is the potential difference across these two, so that's delta V. The potential difference across these two is going to potential difference across these two, so that's also delta V. These are connected in parallel. So my equivalent capacitance, C equivalent, is just going to be C1 plus C2. Okay? Then they're asking for, what is the capacitance in terms of the quantities. So they also give you the surface area. So the surface area of all these plates is just A. So I can write the capacitance of the first one, that's epsilon naught, A divided by D1. The capacitance of the second one is epsilon naught, A divided by D2. So the equivalent capacitance is just the sum of these two. And that comes to epsilon naught A D1 plus D2 divided by D1 times D2. Okay? So this will be the equivalent capacitance in terms of the quantities given. All right. Then we let this middle plate move up and down. So this is going to change D1 and D2, but their sum is going to be fixed. So I'm going to call that sum D1 plus D2 to be just D. Okay? And they're asking for what's the minimum and maximum capacitance values of the net capacitance. Okay? So I'm going to express everything in terms of just one of the variables. So in principle, this depends on both of these variables, D1 and D2, but because we have this additional equation here, that reduces, gets rid of one of the variables. So I can write, for example, D2 as D minus D1. So that expression over there and becomes epsilon naught A, this is just D, divided by D1 times D minus D1. Okay? Now what's the maximum and minimum of this expression? Well, the maximum is easy to see. We can actually move this plate, up to here or down to here, so we can just make just this middle plate almost touch the upper plate or the lower plate. In that case, either D1 or D minus D1 becomes 0. The denominator becoming 0, this is just going to become infinity. That's, of course, as large a capacitance as you can get. The other one, what will be the minimum? For that, let's take a look at the denominator. That's the only part that depends on the variable D1. So this is D times D1 minus D1 square. So in terms of the variable D1, this is going to look like an inverted parabola. Okay? And it's going to have a single maximum. That single maximum we can find by taking derivative of this with respect to D1 and set it equal to 0. So derivative of this with respect to D1 is D minus 2 D1. That being equal to 0 is going to be D1 D by 2. So when this plate, middle plate, is at the midway between the two other plates. So that would correspond to the maximum of this parabola. That being in the denominator is going to correspond to the minimum of the equivalent capacitance. The maximum, as I've said before, is just going to be infinity when D1 is equal to 0, or when D1 is equal to D, corresponding to D2 is equal to 0. And I believe that's all for this problem.